Today, dealing with the theory on how to design nuclear reactors, we have built up the mathematical background in the last two lectures. We have described the interaction of neutrons with materials in general. We defined the neutron cross-section for different materials. We defined the neutron flux, which is the equivalent of temperature or voltage or hydraulic head in other fields of endeavor. It's a scalar quantity. And when it is vectorial, it becomes named the current. Today, what we'd like to do is use the neutron diffusion equation that we derived last time, diffusion, because it assumes the behavior akin to the diffusion of matter according to Fick's law. Today, what we want to do now is try to cover the theory on how to deal with neutrons interacting with materials that are not multiplying. So that's a theory of interaction of neutrons with non-multiplying media. Non-multiplying meaning that the medium does not contain fissile material that would multiply through fission the number of neutrons. So we go there and start sharing right away. And the chapter that we are interested in today is the chapter on reactor theory. So we go to reactor theory, transport and diffusion reactor theory, and we deal with neutron diffusion in non-multiplying media. When we have a fissile material that fissions and generates neutrons, we are going to call this a multiplying medium. And you'll find that the mathematical description is very, very different than the one for non-multiplying media. In non-multiplying medium, the mathematical problem is what's one of a source problem. So that's like solving a linear system of equations where you have an operator operating on a vector and equaling a vector on the right-hand side of the equation. In multiplying media, you'll find that the source term or the right-hand side of the linear system depends on the solution itself. So we don't call that a linear system of equations anymore. It is an eigenvalue problem. And the eigenvalue determines the criticality of the system. So you find that we have two chapters here, neutron diffusion theory, and it will split into diffusion in non-multiplying media and diffusion in multiplying media. So let's start with the non-multiplying media. So in non-multiplying media, we said that we don't have a fissile material. And in that case, if we consider an experiment in which we have a beam of neutrons, I sub 0 here, intensity, that would be neutrons per centimeter squared per second, or the number of neutrons crossing the unit area per unit time, and that it interacts with a small target of some material of thickness x. The neutrons are going to interact with the nuclei of the medium. They're not going to be affected by the electronic cloud since the neutrons have no charge. Some of those neutrons will be absorbed, but most of them will scatter. And this is shown by those arrows here scattering away from the beam. So the beam intensity by that scattering and absorptions. Notice that we don't have a multiplying medium, so the neutrons are not going to multiply. In that case, you find that the beam intensity I sub 0 becomes I of x, and it is attenuated. And in the same way, like in the chapter on the interaction of gamma ray radiation with matter, we find that the attenuation is exponential, meaning that after a given length, you'll find that the beam intensity is reduced by 1/2. So I of x here, the intensity of the outgoing beam, if we have a detector measuring the intensity of the beam, will follow an exponential. And the same exponential, in fact, as in gamma radiation, except that in gamma radiation, instead of that macroscopic cross-section, total macroscopic cross-section, sigma sub t, we have the mu, or the mu, we called it the attenuation coefficient for gamma rays. So basically, I of x is going to decrease exponentially as a function of the distance x, same as gamma radiation. Incidentally, also the same as radioactive decay, except in radioactive decay, the variable here is not going to be the distance x, but the time t. Notice here that the macroscopic cross-section is calculated by calculating the number density of the material, n here. This is the modified form of the fixed law. By dividing into the volume, we use the density. So it gives us immediately the number of nuclei of the material per unit volume. And you multiply that by the microscopic cross-section, which has units of centimeter squared or barns, you'll find that the units of sigma total is 1 over centimeter. So we can rewrite that equation in terms of the inverse of the total macroscopic cross-section, and that would be the mean free pass, the total mean free pass. And it has a physical meaning. The physical meaning is going to be that it is the distance traveled between two interactions of the neutrons in the material. It could be scattering, could be absorption. Today we are not dealing with fission, but it also applies to fissions if we do not seek the calculation of the criticality. So N here, we have dealt with that in the previous chapter, and it is a modified form of fixed law. It's rho here rather than the g, the mass of the material. Notice that when you deal with the exponential function, the argument of the exponential should be dimensionless. So if your lambda sub t here is in centimeters, or sigma total is in centimeter minus 1, your x should be in centimeters, so that you make the argument of the exponential dimensionless. And in that case, if I have a certain beam intensity, we are really interested in the inverse type of a problem of mathematical physics. Yeah, we can calculate how much the attenuation of the beam is. I'm given a distance x. But the real design problem is to determine x, given that I have an attenuation that I want in my design. And the attenuation would be the I of x divided into I naught. So we take the logarithm, natural logarithm of both sides. This would be the attenuation of the beam here. It could be by 1,000,000 times, by 1,000,000,000 times, 10 to the minus 9. And when we take the logarithm of the exponential, we get the argument of the exponential. We bring it to the left-hand side, and you find that basically x, the distance that would attenuate the beam by a factor of 1,000,000 10 to the minus 6, or 1,000,000,000 10 to the minus 9, is given by the minus 1 over the total macroscopic cross-section, the natural logarithm of the attenuation. Notice here that compared with gamma rays, we do not have a build-up factor. So the equation is simpler in form, but it takes the same format. And in gamma rays, mu, the attenuation coefficient, replaces the macroscopic total cross sections. In fact, that equation is the equation measured, used to measure those cross sections that we have dealt with before. So instead of solving for x, the distance that would shield humans, obviously, against radiation, we can solve for the sigma here, expand your macroscopic total cross-section into the product of the number density multiplied by the distance x, bring the x to this side, get the sigma total to this side there, and you could see how tedious the job of those people who work so hard to provide us with the data of the cross-sections work. They had to get a beam of neutrons at a given energy, at a given intensity, let it interact with all the isotopes that we know of, calculate the attenuation, and then tabulate and create data sets or data warehouses for us to use in our design calculation. So that's how sigma total would be estimated. Remember the equation now for that we derived last time, the time-dependent equation for the diffusion of neutron, the continuity equation on any arbitrary volume capital V was equal to the partial derivative of the number density by dt, and that was equal to the source of the neutrons, the source strength, minus the, so this is a positive term, minus the absorptions, minus the divergence of the current normal to the surface. Remember, this would be a negative term. This is a loss term in the equation. So source minus absorption minus leakage is equal to the rate of a change in the number density. But we have calculated we have rederived the equation and made the change of variables in terms of phi, the flux. So in that case, it becomes 1 over V, the d phi partial by dt. Then came Mr. Helmholtz, and we used his equation, and that would be the steady state form of that equation. Remember also that we use Fick's law to suggest that the current, which is integrated over the surface to estimate the leakage from the surface of a reactor or any shield, was equal to minus d, the diffusion coefficient, the gradient or the flux of the flux, or the slope of the flux. In Cartesian coordinates, it's a partial derivative. The gradient of the flux is a partial derivative with respect to x in the x dimension, plus the partial derivative with respect to x, the y in the y direction, and the partial derivative of phi with respect to z. Notice here that the gradient is always acting on a scalar. So our flux here is a scalar function, same as temperature in heat transfer, same as voltage in electronics and electromagnetics, same as a hydraulic head when we deal with hydraulics in general. It must be observed that taking the gradient adds a negative to something that's a loss, the leakage from the surface. So negative gives us a positive, but in fact, we have to always remember that that term here in the diffusion equation for neutrons is a loss term. Now, if d is a constant, we can take the d outside the divergence operator, and we end up with the divergence of the gradient. What's the divergence of the gradient? The divergence of the gradient is what we call the Laplacian, the del square operator in general. Okay, let's take the steady state diffusion equation, which is the Helmholtz equation. Then the partial derivative with respect to time vanishes, and we get the equation that describes the steady state operation of any neutrons interacting with materials or in a nuclear reactor. You can prove that the divergence of the gradient is equal to the Laplacian operator by taking the flux here, the component of the flux, and take the divergence operator. The component of the flux in the x direction is d partial phi by dx, in the y direction d partial phi by dy, and in the z direction d partial phi by dz. And when you take d partial by dz, d phi by dz, oh, you get the del, d square phi by dz square. Notice this is a partial differential equation in the space x, y, and z, the Cartesian coordinates, and the equation takes different forms depending on whether we have a Cartesian geometry like a cube, a parallelopiped, or a cylindrical geometry, or when we deal with a sphere. We'll start by dealing today with a sphere because it gives us the simplest solution to the problem. As we take the Helmholtz equation, you'll find that now we have d del square phi of the flux in the x, y, and z dimensions, minus the absorption rate. When you multiply the absorption macroscopic cross-section into the flux, you find that you get units of neutrons per centimeter cube per second. This is the absorption rate, and this is the source of neutron that we are trying maybe to shield around. Well, we can simplify that further by dividing into d. So let's divide that equation number 8 by d, and you end up with del square phi x, y, and z minus sigma absorption divided into d is equal to minus s over d. We have seen that equation in all other fields of engineering, and you had classes in mathematics that started solving that equation. So we are not going to reinvent the wheel. We are going to see what solutions we can get from other fields of science and engineering to solve for that flux phi. We want to know what is the flux. Why? Because when I multiply the flux by the fission cross-section instead of the absorption cross-section, I get the fission rate per unit volume of the fission rate density. If I multiply it by the energy released by fission, that is the power. And engineers and physicists, of course, study and want to control the power generated by a nuclear reactor. If we take that sigma sub A divided into D, the dimensions of sigma sub A is centimeter minus 1 or 1 over centimeter. D has units of centimeter. So you find that that D over sigma A has a physical meaning. It has the dimensions of a square of a length. So we take that length and call it the diffusion area. And obviously, this is an area here, L squared. And when you take the square root of L squared, it's a dimension of L in centimeter. This is, has a physical meaning that it is a distance traveled by a neutron in a medium from the time it is born in the source to the time where it is either absorbed or leaks out of the system. So we can rewrite that equation, the Helmholtz equation now, for neutrons in an even simpler shape. Del square phi of x, y, and z minus 1 over L squared is equal to minus S over D. S is the source and D is the diffusion coefficient. And at that point, we may like to stop and see what kind of solutions we can get to that differential equation. Before we do this, we take the simplest situation where we have maybe a nuclear reactor on a spaceship with a nuclear reactor taking us to Mars or to Venus or even to the moon. The use of a nuclear rocket would give us a very high specific impulse. So the mission time would be 2 to 3 weeks rather than a year or more, where the astronauts and the spaceship can be hit by solar flares and basically the astronauts killed, or the instrumentation and the engineering system on the spaceship damaged. So in that case, we are going to think, and NASA is indeed thinking about nuclear propulsion in space for a trip to Mars or to the neighboring planets, maybe beyond the solar system, who knows. The first simplest solution for the flux can be exemplified by a source of neutrons that does not interact with the medium surrounding it. So the neutrons are coming out from the source of neutron, and this example, as I suggested, is a nuclear reactor on a spaceship, and you want to shield the crew against the radiation. It would be also in astrophysics the radiation from a neutron star. If we assume that the neutrons move in space that is a vacuum, they do not have any medium to interact with. So what do? They move in a straight line. This is the process of what we call streaming. And that happens to light in the atmosphere if it doesn't have to interact with the molecules of nitrogen or oxygen or carbon dioxide or water. And the process of streaming also describes basically a source of water coming out from a stream. That's why we call it streaming. So what is the neutron flux at a distance r from the source? In that case, we all know that as the distance increases, the surface area of a sphere surrounding the source also increases. So the intensity of the number of neutrons crossing unit area per unit time, which are the units of the flux, is going to follow what we call the inverse square law. You could see here that the flux in that case should be equal to the strength of the source, neutrons emitted per second, and divided into the area of the sphere at a distance r. And we know that the surface area of a sphere is 4 pi r squared. So as a function of distance from the source in a vacuum, you'll find that the flux has a very, very simple solution. You know it from experience. The farther you are, say, from a storm, you'll find that the lightning light decreases in intensity. The farthest stars from us are more faint than the closest stars to us. And it also applies, in fact, to sound. The farther away you are from the sound, the less intensity you can feel, because, of course, the sound and the light are basically spreading themselves over a larger distance. So for a vacuum, for neutrons, they simply stream, and the neutron flux is equal to S over 4 pi r squared. Very simple solution. The difficulty comes in when we have a diffusing medium. So if there is a medium here, like on Earth, where you're using, say, shielding, concrete or steel or water to shield against neutrons, the neutrons are not going to move in a straight line. They'll encounter a nuclei, and they can get absorbed, they can scatter, and they undergo reactions in general. And we said that the underlying equation is that simple del square phi minus 1 over L square phi is equal to minus S over D. So this is our modified form of the Helmholtz equation. Now, that equation arises, of course, in the field of shielding against neutrons, but it has been seen and has been studied by the mathematicians and the engineers and the physicists in other branches of engineering. So we're not going to reinvent the wheel. We are going to adopt the solutions for that equation and then stick it to the interaction of neutrons with matter. So the problem that we are going to solve now is a source of neutron interacting with a medium as a shield of radius r, but then it is not a vacuum anymore. So the neutrons are going to scatter, they're going to get absorbed, but not causing fission. This is still a non-multiplying medium. That medium is going to be characterized by diffusion lengths in the Helmholtz equation and by a diffusion coefficient. The diffusion lengths have units of centimeter, and the diffusion coefficient also has units of centimeter. So let us then adopt some knowledge from other fields of science and engineering to solve that second order differential equation. Now, you have seen this earlier in classes like Physics 108, for instance, but for the benefit of those who have forgotten it, we are going to establish the analogy between our equation for neutron diffusion and other second order differential equations that we encounter in other fields of science and engineering. The simplest equation that resembles our equation is the equation of what we call the simple harmonic oscillator. So in that case, we take an experiment in which we have a mass m of any material on a plane and attached to a spring, and the stiffness of the spring is K. So, and we ask ourselves the question, what will happen to that mass if we pull it to the right along the positive x-axis away from the equilibrium position? So I pull it this way, delta x here in this direction, and try to describe the motion of that mass. This is called the simple harmonic oscillator equation. You can go back to your Physics 108 and revise it maybe in a different format. What are the forces that we have on that mass? First, the spring is going to try to pull it back to its equilibrium position from, if we pull it away from the equilibrium position. So we have a force here that is proportional to the stiffness of the spring and also proportional to the distance that we pull that mass away from the equilibrium position. So you'll find that it would be in the negative x, positive x direction. So that force exercised by the spring is minus kx. There's another force that that mass will be subjected to, which is the friction with the plane here, whether it's glass or wood or steel, there is a friction, and that friction resists the motion the same way that the spring is trying to restore the mass back. That friction resists the motion also in the negative x direction, except that that force of friction is not proportional to the distance in which we pull the mass, but it's proportional to the speed or x dot dx by dt, in which the spring is, the mass is moving on the surface. So now in that case, we have two forces, the spring restoration force minus kx and the friction on the plane minus beta x dot. And these have to be equal to the mx double dot, m being the mass of the of that little mass here, m, and x double dot, of course, is the acceleration. That's Newton's law. The forces have to balance out. And when we solve the equation that describes that system, which says that m dot x double dot is equal to minus kx and plus minus beta x dot. So we wrote the equation here. This is a simple differential equation. Mx double dot is equal to minus beta x dot. That's a friction factor here. K is the spring stiffness. And you have seen that equation, of course, in that simple problem. The solution for it is that we go there, make an assumption that we don't have much friction. So if we take a special case, this is a special case where the plane has no friction, then mx double dot is equal to minus kx. We divide both sides into m. So x double dot is equal to minus k divided into mx. And that k over m is a very interesting kind of a constant. We call it omega square. Why is it omega square? Because that omega is the square root of the omega itself. So square root of omega square is the square root of k over m is equal to twice pi the frequencies. This means what? This means that the the spring is going to oscillate according to the solution of that very simple second order ordinary differential equation. So what is the solution to this? X double dot is equal to minus omega square x. The solution basically is a harmonic solution, or the spring is going to oscillate. Remember, oscillate because there is no friction. So it will keep on vibrating or oscillating around the equilibrium position forever until the spring, of course, heats up and dissipates the motion. So what is the solution to x double dot is equal to minus omega square x? We have learned in other courses that that is a harmonic solution. So the position x as a function of time is cosine omega t plus sine omega t. And we add two constants because we have a second order differential equation. We need to determine the values of those two constants, a and b. Another form of that solution, harmonic solution, that electrical engineers like to use is using the J quantity, which is in fact in mathematics I, the square root of minus 1. Why? Because cosine omega t plus sine omega t is equal to the exponential of E plus J omega t. And the minus here, cosine minus J sine omega t is equal to E to minus J omega t. So in that case, the cosine here is the sum of those two exponential divided into 2, and the sine is the difference between the two exponential divided into 2. So whenever we see that x double dot is equal to minus omega square x, we know from mathematical physics that the solution is x of t is equal to a cosine plus b sine omega t, or we can take the form of the exponential, and we have a complete solution to when we determine the values of a and b. Notice that's a prime and b prime because the constants would be different depending on which solution we adopt in solving our problem. Wonderful. Now, is there another analog to that equation? Yes, definitely the spring constant is of interest to our physics majors and our civil engineers, our mechanical engineers, but we have also the electrical engineers. So let us see how we can establish some solution that we can use in solving our second order differential equation. If you get a tuning circuit as in a simple description, you can think about a circuit that has three components, an inductance, a capacitance, and a resistor with a voltage applied from a battery here at the bottom of voltage capital V. Now, the capacitance, of course, stores energy there. Energy in the capacitor is stored in the form of an electric field between the two plates of the capacitor. If you have an inductor and you have a coil basically here, you find that the energy is stored in the inductor in the form of a magnetic field. So you rotate the coils here, you get a magnetic field along the length of that cylinder. However, R is a dissipative element. R here, a resistor, turns the electrical current from the equation I square R into heat. So that's a dissipative element. And if you remember your classes in in circuit analysis, you'll find that we can write the differential equation for that tuning circuit as the voltage as a function of time being equal to the inductance d square q. Q is a charge by dt squared plus the resistance multiplied into the current dq by dt plus q over c in the capacitor. Let us again assume that we have an ideal situation where we don't have a resistor, so no dissipative element. So the equation becomes simpler. You get C, the capacitance, and L, and you can withdraw the voltage. The voltage would have created a field between the plates of the capacitor and the magnetic field along the coils of the inductance. And in that case, the equation becomes, if we drop the R term in the differential equation, we get L d squared q by dt squared is equal to minus q over c. Bring the L to this side and you get, oh, here's the same as the x double dot is equal to minus omega square x, except that is now q double dot. The charge is going to oscillate. And in fact, if ever somebody can create that ideal circuit, maybe by having a resistor that becomes superconducting, you'll find that that system oscillates. You'll find that the energy stored in the capacitance moves into a magnetic field of the inductance, and then the energy stored in the magnetic field in the inductance moves back to the inductance. You can also write another equation, which happens in the same way, of the pendulum, where as you move the pendulum right and left, its kinetic energy at the bottom of its movement becomes potential energy at the end of its movement, and then the potential energy turns back into kinetic energy, then into potential energy, and so on. And on a Tuesday, find your way to the Museum of Science and Industry in Chicago. The entrance on Tuesday is free, so you'll find that teachers take their high school and even grade school want young people to visit the museum, and they have what's called the Foucault pendulum there. You could see the Foucault pendulum that describes the rotation of the Coriolis force, that is the force caused by the rotation of the Earth. Both the two equations for the mechanical system, I didn't deal with I can ask you to deal yourself with the pendulum, maybe equation where kinetic energy and potential energy are exchanged. But in either case, either solution has that oscillatory solution. So you find that the system basically oscillates, and the solution is A cosine omega t plus B sine omega t. Well, okay, the solution that we sought here is a solution that has a negative sign here. What if we have a positive sign? You may or may not have dealt with that before, but if you have a positive sign, the differential equation becomes very different. It becomes a situation of exponential growth or exponential decay. So with a positive term here instead of a negative term, the solution takes a shape of a hyperbolic cosine plus a hyperbolic sine. So we write here e to the plus omega t, and we write here e to the minus omega t. Notice that the j here, the square root of -1, does not appear in that case. And we can say that these two equations are equivalent because e to the plus omega t is a hyperbolic cosine of omega t plus a hyperbolic cosine of omega t, and the hyperbolic cosine of omega t minus the hyperbolic sine is equal to e to the minus omega t. So in that case, you'll find that we can use those two pieces of information from mathematical physics. And we go back to where we started earlier in the chapter. Remember, we said that the equation that describes the neutrons diffusion in a medium that is non-multiplying is not going to be like in the case of a point source. This is spherical geometry in an infinite medium, and there is no absorption there. That's the inverse square law, S over 4 pi r squared. We really have to solve that differential equation right here. Not as though that it is a second derivative, but it is not a second derivative in time. Like when you say x double dot or q double dot, that is d by dt squared. However, the fascinating thing here is that for a nuclear reactor, the distribution of the flux here as a function of position in the reactor, or the power distribution later on, follows a second derivative in space, in r, not in t. So what do? We take the solution that's in t and we replace the t by r. Oh, we get the solution for the neutrons interacting in a shield material, and later on in a nuclear reactor. So there is a fascinating analogy here between the simple harmonic oscillator or the damped oscillator in mathematical physics, in our case of neutrons interacting with a medium. Now, we are going to, for comparison with the point source in an infinite medium right here, we are going to also adopt spherical geometry, and we are going to solve the differential equation. And in that case, the first step in solving a differential equation is to choose up the form of the Laplacian. It takes different forms, as we said in the last lecture. Whether you have a Cartesian coordinates, whether you have cylindrical coordinates, or whether you have spherical coordinates. So our del square takes the form here of the spherical coordinates Laplacian, which is 1 over r squared, d by dr, r squared d phi by dr. And it is not a partial derivative because it depends only on one variable, the distance r. And let us ignore for temporarily that minus s over d. And you notice that if you bring to this side that minus 1 over L squared, you end up with the equation that looks like the damped harmonic oscillator, which was x double dot is equal to plus omega square t. And in that case, we know immediately that we can use that solution in determining what is the solution for the neutron flux that results from a source of neutron in an infinite medium. We are assuming it's infinite in size if there is a material there that we are shielding against, non-multiplying. So let us find what's the solution for that equation right here. Well, the fact that we have the spherical geometry in the Laplacian leads to a little difficulty that invokes the art and the science of solving differential equations. Mathematicians for a long time have helped us engineers and physicists by telling us that whenever you have that form of the Laplacian, you'll always find a solution that is a function of 1 over r, 1 over r. So in that case, we are going to get that piece of knowledge into consideration. We're going to do it in detail today, but when we get to the multiplying medium, when we evolve into the multiplying medium, we are going to use it and not go through the detail. So in that case, the mathematicians tell us as engineers, okay, replace the flux, make a change of variables in the terminology of mathematics of that phi of r being equal to some function of r, let's call it w of r, divided into r. Why? Because the Laplacian always leads to 1 over r dependence. Now we have here terms phi of r. Oh, so we substitute here w over r for a change of variables. But we have d phi by dr here, and then we multiply it by r squared and take another d by dr derivative. So to take the d phi by dr and substitute in that equation, we meet a little difficulty in that the numerator is a function of r and the denominator is also a function of r. So we can think that we can split them into w of r multiplied into 1 over r and apply in that case what's called the chain rule of differentiation. So if you have two functions u and a further function v that are both a function of x, d by dx, the product of the two functions of x is the first term u multiplied by the derivative of the second dv by dx plus the second term v multiplied into the derivative of the u by dx. I'll repeat again. It's the first term u dv by dx plus the second term multiplied by the derivative of the other term. If you take the solution, the assumed solution for the change of variable that's w multiplied into 1 over r, you take the w first, multiplied into the derivative of 1 over r. d by dr 1 over r is minus 1 over r squared. And then you take the second term 1 over r multiplied into the derivative of the first term, which is dw by dr. In the differential equation for the source of neutrons, we have here r squared d phi by dr. So you multiply that d phi by dr by r squared, and then we take its derivative. So r squared multiplied into d phi by dr becomes the r squared, and the r squared cancel. And here r squared cancels with r, provided, now be careful, very careful here, provided that r is not equal to 0. Why is that? Because when r divided into r at 0 is not equal to 1. It's an undetermined quantity. So we put here the symbol from mathematics for all values of r not equal to 0. This means that our solution cannot apply at r is equal to 0. And that's what some people in science fiction call it singularity, because it leads to an infinite solution, basically. All right, so we take now r squared d phi by dr, and we take its derivative. We repeat the chain rule of differentiation. That's a difficulty that we are meeting today. We take the first term r squared, of course r squared d phi by dr, we have already determined is equal to minus w plus r dw by dr. So the first term derivative minus dw by dr is simple, but the second term, now we take the first term r by the derivative of dw by dr, the second term d squared w by dr squared, plus the second term dw by dr by multiplied into the derivative of the first. dr by dr is 1. Oh, that is something interesting here. That term here and that term here cancel, and we are left with r d squared w by dr squared. So that whole term in the Laplacian, 1 over r d squared d by dr, r squared d phi by dr is equal to that 1 over r now, because we divide into r squared that term. So the r and the r squared cancel again for all values of r not equal to 0. This means that the solution is not going to apply at the origin. It's a singularity, as we called it. So for in that case, you find that in the expression for the Laplacian as a solution for the w function, you find that we have 1 over r d squared w by dr squared minus 1 over l squared w over r. Okay, it looks nice. R and R cancel again, provided we are not at the origin. And we end up with d squared w by dr squared is equal to plus 1 over L squared w. Okay, well, looks very much like now mx double dot is equal to plus omega squared x. So plus here means that we have to adopt the exponential growth and decay equation, not the sinusoidal, not the harmonic solution, that's cosine plus sine. So what is w as a function of r in that case? It's either that we take the hyperbolic sine or the hyperbolic cosine, or we said that we can take just a positive exponential, e to the plus r over L, and as well as a negative exponential, e to the minus R over L. Well, but we said initially that the flux was the solution W of R over R. So in fact, in that case, the whole solution phi of R by introducing that change of variables is a constant of integration, a negative exponential divided into R, plus B, a second constant of integration because it's a second order differential equation, e to the plus R over L over R. And if you take the first derivative and the second derivative and go substitute in the original equation, you'll find that that solution does satisfy the original ordinary differential equation. And mathematicians basically are now very happy with that solution. They start proving basically that it converges, that and so on. But for us engineers, we are mostly engineers in our group, and we find that we deal with real world solutions. So we need to now determine what are the two constants of integration A and B. And in the real world, we know that our flux cannot become infinite. And the exponential function, if it has a positive sign here, grows up exponentially. So there is no way that our neutron flux is going to become infinite in value. We cannot have an infinite number of neutrons crossing the unit area per unit time. So what do? We adopt a real life solution. That's why engineers can call themselves applied mathematicians. We deal only with the real world solution. So in that case, immediately we can say that B here, the gross solution does not exist. And we drop that B. Basically, we say that B is 0. And the solution for the flux for our source of neutron of strength S in an infinite medium is equal to a constant of integration 1 over R. The flux is going to decrease both as a function of 1 over R distance from the source, and also as a function of a negative exponential, and we take the ratio of the two. Okay, partial differential equation of second order at two constants. We use basically a real world solution. We said B is 0, but we are left with A. How do we determine A? We go back to electromagnetics. We adopt the idea of what's called the pillbox approach. You can use the operator approach and prove the same thing. And we say that as we take the current, in that case, over the surface of a sphere, as the sphere tends and becomes 0 at the origin, as R tends to 0, and that should be equal to the strength of the source in neutrons per second. So if we take the current, according to Fick's law, G of R multiplied by a surface of a small sphere, that gives me the number of neutrons leaking from the system per unit time. And when we take the limit mathematically of R tending to 0, we should get the capital S. Well, the difficulty here is to determine what is the current. The current, according to Fick's law, is minus D, the gradient of phi. And phi, as we said, is equal to A e to the minus R over L over R. Now, this is, again, the A constant can come out. So I get minus dA here. But then I have two terms like UV. One function 1 over R multiplied into e to the minus R over L. Again, a second time today, we apply the chain rule of differentiation. We take for d by dr of that product of those two functions of R, we take the first term, 1 over R, multiplied into the derivative of the second. The derivative of the exponential gives me the exponential itself again. And then we take the derivative of the argument of the exponential, which is minus 1 over L. Then we take the second term in the chain rule of differentiation, which is the V here. That's e to the minus R over L multiplied into the derivative of 1 over R, which is minus 1 over R squared. We simplify the terms and you find that the minus sign comes out here to be a plus sign for the current. And then you end up with 1 over LR, the negative exponential, and then another 1 over R squared, again, the negative exponential. So now if we take the J of R here, multiplied into 4 pi r squared, the small sphere that shrinks to 0 at the origin, you find that 4 pi r squared, you get the 4 pi out here, and the r squared and r squared cancel, provided that r is not equal to 0, and you then get also r squared divided into r. When you take the limit as it tends to 0, you find that the second term basically vanishes, and take the limit r equal to 0, that term vanishes. That term also is multiplied by a negative exponential, so it also vanishes. And in that case, you'll find that the limit as r tends to 0 should be equal to s, the source of genera. So in that case, you find that 4 pi dA as r tends to 0 is equal to just s. All right, that term is actually the limit as r tends to 0 is r here 0, so that's 4 pi dA, and we said that that limit is equal to s. So 4 pi dA multiplied into unity here, because the exponential function, when r tends to 0, if you draw that exponential function, you'll find that it comes down this way, and at 0, it is equal to 1. So s is equal to 4 pi dA, and consequently, we can solve for a, which is s over 4 pi d. Now, we said that the solution was a multiplied into the negative exponential divided into r. So we have a solution for the flux as s, capital S, 4 pi d r in the denominator, and an exponential e to the minus r over L in the numerator. Let's compare this very quickly to the case of the non-multiplying medium. In the non-multiplying medium, we got s over 4 pi r squared. So the r squared in the medium that is infinite and in a vacuum, actually, the vacuum, you'll find that instead of r squared, we have the diffusion coefficient replacing one of the r's. But in addition, the second r squared is replaced by a negative exponential. And in that case, you can basically plot that, use a hand calculator or use a computer procedure here written in Fortran. And we can plot that flux as a function of time away from a source S. And you could see here that you have not just a decreasing exponential at a distance s from the source, but it's a negative exponential divided into r. But then you have to be careful when you write a computer program in that case, because mathematically we said that the solution applies everywhere except at r is equal to 0, which is a singularity, because you could see here it tends to 0. So in a computer program, if you try to calculate it at 0, it would give you a fatal error. And you have to be careful tying up any computer results to really the mathematical result that you are dealing with in general. All right, so this is the situation for a medium in which we have a point source in a non-multiplying medium. And the comparison is to be done in a medium that is a vacuum. The solution is one, the flux is equal to the source divided into 4 pi r squared. Let's go back to this again, just in summary, all that work here to prove that for a particle in a vacuum, the flux at the distance r is the inverse square law, s divided into 4 pi r squared. If somebody asks me what is the current is going to be in the same direction as the flux, except that it will, in a vacuum, basically the current should be equal to the flux. There is no diffusion coefficient, there is no absorption cross-section. Whereas if we have a medium with a diffusion coefficient capital D and absorption cross-section and the diffusion lengths, we found that the flux now takes a different form, which is that S divided into pi d 4 pi dr, and with an exponential e to the minus r over L. Now notice here that the current is not going to be equal to the flux. The currents would follow will follow Fick's law. So the current would be minus d, minus d, the gradient of the flux. And I'll give you a problem where you will make sure that you differentiate between current and flux. When in a vacuum, you'll find that the current and the flux are equal. And remember that the current is vectorial. It takes a direction. Whereas in the case of the flux, it just adds up. When you have a temperature or voltage, they add up in a scalar way. But when you get an electric field, that's a gradient of the voltage. Or if you get a heat flux, that's a gradient of the temperature. Then they add and subtract each other in a vectorial way. And that's why I'll give you a problem today, maybe in which you would simply take a geometry, a line or a cube or an equilateral triangle. And let's see where the problems are, and calculate the current and the flux and make a distinction between current and flux. That can be a life savior because you may have a situation like, let's take the electrical engineers, where at the maximum point in the distribution of voltage, your current could be zero because two currents in different opposite directions can cancel out. But then because the current is zero doesn't mean that the voltage is not very high, and it can fry you. It can literally fry you. Same for neutron flux. At the center of a nuclear reactor, you'll find that the flux and the power reaches a maximum. So the current there is zero, but it doesn't mean that there is no power and no neutron flux generated at the center. Same for temperature. You may have a gradient in temperature in a measuring from a measuring device that tells you that basically the heat flux Q double prime is zero, but you can have an extremely high temperature that can also fry you in general. So today I'll give you a problem on that chapter where you take a shield and see how you can attenuate neutrons from a shield. This is a very major design problem if you deal in any kind of nuclear reactor environment. And then here we take maybe a square, a cube, or equilateral triangle and calculate the flux and the current. Remember, a current is a vectorial quantity, so two currents in opposite directions cancel out. That'll become zero. But sources give also a flux, and the flux in that case is a scalar quantity. It adds up in a scalar way. So I'll basically will try to understand this idea by solving a problem, simple problem of a line source, maybe, that I'll give you for today's work. I will go to the chat room and allow for any questions. Today is very mathematical, but we could see that we have also some very important design consideration to take into account. No questions. So we suggested earlier in the lecture that we are going to deal with two different types of problems mathematically. One that we are going to call the multiplying medium, and one is a non-multiplying medium. The medium that we dealt with arises maybe in applications of shielding against radiation. So you determine the thickness of a shield that would attenuate your neutron flux by a certain attenuation factor. We know how to do that now. We also know that there is a difference between the current and a flux, and a current can be zero, but the flux can be very large. So keep that in mind if you are an electrical engineer or you are deal with heat transfer. Your temperature can be very high, by the heat flux could be zero, and the voltage can be extremely high, but the current can be zero if considering the vectorial properties and as well as the scalar properties. Nuclear reactors, though, operate with fissile material. So as the neutrons interact with the materials, they cause fission, and fission generates neutrons. So in that case, we call the medium a multiplying medium. And we go there, and today we learn the difference between a multiplying medium and a non-multiplying medium. And the dealing with the multiplying medium is really the secret of the nuclear age. So your group of engineers becomes privy to the secret of the nuclear age. And that becomes really the topic of one group reactor theory. One group is a terminology used to say that we are going to consider the neutrons not divided into fast, intermediate, and thermal neutrons, but we'll take them all as thermal, and that's what happens usually in nuclear light water reactors, the pressurized water reactor and the boiling water reactor. Again, we started with the neutron diffusion equation where losses are equal to gains, and we took the steady state solution, dN partial by dt is equal to S minus the absorption rate minus it is plus the leakage from the surface. However, in the multiplying medium, we don't have a source of neutrons that's emitting a constant number of neutrons per unit time. The source in the nuclear reactor depends on on phi, on the flux, the source itself. And we go back and invoke our very famous Oklo phenomenon. That's why we spent some time on it and figure out what is the description of that capital S. Before we do this, because we are going to carry out some actual calculations before the end of the lecture for a critical mass, the diffusion coefficient usually is taken as 1/3 the scattering mean free path, which is 1 over the macroscopic scattering cross section. Sometimes we make a correction from the more advanced transport theory. So in actual calculation, we replace the scattering cross section by what we call the transport cross section. So the transport cross section is that scattering cross section multiplied by 1 minus mu sub 0, mu naught sub average. And that is the average of the cosine of the angle of scattering. That's why it's called transport theory. It's a correction where simply we take that mu average 0 as 2 divided into the 3 times the mass number of the isotope. So mu naught average is 2 divided into 3a. And that correction basically turns Fick's law into more applicable to existing nuclear reactor applications. In the Oklo phenomenon, when we studied it, we suggested that neutrons behave like bacteria, they multiply. And we defined what we call the multiplication factor as a neutron produced in fission generation divided by the number of neutrons in the previous generation. You can think about bacteria in a generation divided by bacteria in the previous generation. And that's why the terminology fission comes from biology and fusion also comes from biology. We suggested in the Oklo phenomenon treatment, and that's why you were tested on it too in the second midterm, that for an infinite medium, today we are going to turn it into a finite medium, but for an infinite medium, we have what's called the 4-factor formula, where we have eta describing how the neutrons are regenerated. So that's the number of neutrons born in fission relative to the number of neutrons absorbed in the nucleus. Epsilon is what we call the fast fission factor. Most of the fissions in thermal reactors occur with thermal neutrons, but 5 to 6% of them occur as fast neutrons. We call this a fast fission factor. P is the probability of escaping those very nasty resonance regions, peaks in the intermediate neutron energy range that we observed when we looked at the plots of the cross sections as a function of energy. And F is some kind of an efficiency, which is the number absorbed in the fuel. We call it the fuel utilization factor, divided by the absorption in the fuel plus the moderator plus the structure plus the coolant, everything else in the nuclear reactor. And depending on the values of those variables, my multiplication factor can be less than 1. So in that case, if we have a chain reaction, it shuts itself down. In the Oklo phenomenon, that was when there was no moderation, when the marshy area containing the uranium went dry, and but it can become higher than 1. In that case, we get a critical system. Okay, let's be more quantitative here. F is the fuel utilization factor. It's the absorption rate in the fuel, sigma sub A absorption. That's a macroscopic cross-section multiplied into the flux. So that becomes the absorptions per unit volume of the fuel, divided by all the other absorptions, the absorption rate in the fuel plus the absorption rate in the moderator, capital M, plus the absorption rate in the structure or anything else that you have in your reactor. So you could see it has to be less than 1, and it's some form of efficiency on how your neutrons are being absorbed in the fuel, uranium dioxide in that case. So that is the F. It's a very simple term. The regeneration factor is the number produced from fission divided by the neutron absorbed in the fuel. We couldn't write that equation when we dealt with the Oklo phenomenon because we hadn't defined the flux yet, and we hadn't defined the macroscopic cross-section. We also introduce here nu, that's the number of neutrons born in fission. It varies between 2 to 3, depending on the fuel, whether it's uranium-235 or plutonium-239 or uranium-233 or plutonium-239. But the regeneration factor would be the number produced from the fission process multiplied into the fission rate. Remember here, that's neutrons per centimeter squared per second. This is 1/centimeter, so sigma sub F phi is the fission rate density, or the fissions occurring per unit time, per unit volume of my reactor. So that is the total fission rate divided into the fission rate or absorption of neutrons in the fuel. So sigma sub AF is the absorption rate density in the fuel. You'll find that phi and phi for homogeneous medium, just for simplification, cancels out. So we are left with the macroscopic fission cross-section divided into the macroscopic fission cross-section, the absorption in the fuel, plus the radiative captures, where neutrons are absorbed in the fuel, like in uranium-235, maybe without causing fission. So I will write that as sigma sub gamma for radiative capture. The macroscopic cross-section is the product of the microscopic fission cross-section multiplied into the number density. For a homogeneous fuel, we can cancel the capital N, and my eta can be very easily calculated as the average number of neutrons born in fission multiplied into the ratio of the fission microscopic cross-section to the fission microscopic cross-section plus the radiative capture. The factor sigma sub gamma divided into sub F is called the alpha factor, that's a designation. So in fact, the regeneration factor can get a very simple form as nu, the average number of fissions produced, divided into 1 plus alpha. We are not going to deal today with the fast fission factor or the resonance escape probability. Remember, in the Chicago Pi #1, the genius of Enrico Fermi was that he separated the fuel from the moderator. So he allowed the neutrons to slow down in the moderator to low energies where they can cause better fission than in the fast energy region. In that case, in the moderator, they escape being absorbed. That is the resonance escape probability. All right, so we came back to our infinite medium multiplication factor, and we start writing an expression for the source. Now, notice the source in the Helmholtz equation now is not a constant. It is a function of the flux. It's a function of the absorption rate in the flux of neutrons multiplied into the infinite medium multiplication factor multiplied by the probability that the neutrons do not leak out of our system when they are fast. So we call L sub F here the fast neutron non-leakage probability. Notice again that the source is not a constant. In a multiplying medium, it depends on the absorption rate or the flux of the neutrons in the fuel. And in that case, in the Helmholtz equation, or actually the time-dependent neutron diffusion equation, S now for a multiplying medium, when we have fissile material, is S is equal to that K infinity L sub F, the absorption rate of neutrons in the whole reactor. And we can simplify that equation that's in N, the neutron density, by taking the definition of the flux as NV, and you find that that term 1 over V sigma sub A d phi partial by dt is equal to, here we divide it into also sigma A, so d over sigma A is L squared, the diffusion area, del square, and sigma A over divided into sigma A becomes 1 here, phi, and it cancels with that last term. So we have a simpler equation right there. All right, let's play a little around with that equation to understand its physical and meaning. What does it mean? It means that if I divide further here this equation by L square in that term here, I end up with 1 over phi d partial phi by dt. And then I end up with a very interesting term, minus del square over phi. So that's a second derivative of the flux, or the divergence of the gradient. Now remember, the gradient is the slope. So that del square, the second derivative of the flux, describes how peaked the slope of the distribution of phi is. And in fact, phi has a distribution in a nuclear reactor, as we'll see in a moment. And that should be equal to that K infinity L sub F minus 1 here. We divide it into phi here, divided into L squared. Now the minus del square phi over phi, as I suggested in structural engineering, we go here to structural engineering all the way from Babylonian and Pharaonic times and India and the Indian civilization and the Chinese civilization, where architects built temples, and in the temples they had columns and beams. And if you have a beam that's subjected to a load from both sides, it buckles. So the terminology of buckling that we are introducing now is dependent on d by d phi, the slope of the distribution. So in that term here, we call the buckling, and we adopt the terminology, as I said, from architecture or structural engineering. Now that term here depends only on the geometry, because the flux has a different solution for or shape in a Cartesian coordinates like a cube or a parallelopiped than it is in a cylindrical geometry. Remember, we have different expression for the Laplacian in cylindrical, spherical, as well as Cartesian geometry. So we call that term here the geometric buckling. It depends only on the geometry. I repeat again, it depends only on the geometry. Whereas that other term here on the right-hand side depends only on the material composition. L squared is d, the diffusion coefficient, divided into sigma sub A. Sigma sub A depends on the type of fuel. The diffusion coefficient depends on the water to moderator ratio, and L sub F depends also on the materials composition. So that term here, we call it the material buckling. And you'll see in a moment that if I take the steady state solution to the diffusion equation here, the governor diffusion of neutrons, if I take the steady state solution, that term is a 0. And what does it mean? It means that if I want to get a self-sustained chain reaction that's steady as a function of time, I have to make my material buckling equal to my geometric buckling. And that is the secret of the nuclear age. That simple equation that we have here, it says for steady state, the geometric buckling must be made equal to the material buckling. It tells us a different story for engineers. It tells us that if you have a certain geometry of materials, moderator, coolant, and fuel, you have to match the geometry to the material composition. If you match them, you have a steady state system. dphi by dt is not going to change as a function of time. If you do not match them, you get a situation where the system will shut itself down, or it will never become critical, or it will be super critical, and this means that you have an accident, or the power of your reactor is going to be increasing. So the goal of engineering design in reactor theory is to make that geometry match the material composition. If we do this, we have a self-sustained chain reaction. We can build a nuclear reactor. And unfortunately, also in the case of an accident, then of course that those two terms will not be equal. And in the case of a nuclear weapon also, that you try to make that K infinity as high as possible. So basically you do not apply really anymore that dphi by dt is a steady state or a constant solution in general. And all the rest of the theory that we are going to do today, we call that material buckling equal to geometric buckling, and we adopt the square there. We call it the criticality condition. We are going to play on it and use it to design nuclear reactors. Okay, so what is the criticality equation? What is the secret of the nuclear age? The secret of the nuclear age is this, that we have to make as engineers for a steady state release of energy, controlling our nuclear reactor to produce power, we have to make the material compositions match the geometry. And because we have to do this under steady state conditions, we call the geometric buckling and the material buckling, and stop there. And notice how the fields of science and engineering complement each other. Like we have been talking about the simple harmonic oscillator, that's mechanical engineering, and we are talking about bacteria multiplying, that's biology, and we are talking about geometric buckling, that's civil engineering, and and structural engineering. All the fields of science some kind of complement each other. Okay, so for the design of nuclear reactor, I must make my geometric buckling equal to the material buckling, and we call this a criticality equation or the criticality condition. Now we can rearrange the expression that we derived here and that we call the material buckling. So we take that term here, K infinity L sub F minus 1 divided into L squared is equal now to the geometric buckling or buckling, and rearrange it. And if we rearrange it, we get a term that looks like this. It gets that 1 is equal to the infinite media multiplication factor multiplied into the fast non-leakage probability divided by 1 plus L squared B squared. L squared is the diffusion area, and B squared is what we call the buckling. And that 1 here establishes a situation where we have a steady state. This means that the number of neutrons in one generation is equal to the number of neutrons in the previous generation. And in that case, this is the effective multiplication factor, taking into account that if we have an infinite medium, now the neutrons can leak from the infinite medium as fast neutrons, and they can leak from the infinite medium as thermal neutrons. So we define that 1 now, or identify the 1 in general, as what we are going to call the effective multiplication factor, which is equal to 1 only if the system is at steady state. So another form of that criticality equation is that K infinity multiplied into the fast non-leakage probability multiplied into the thermal non-leakage probability, which is now 1 divided by 1 plus L squared B squared, should be equal to the effective multiplication factor in general. So it is 1 in the steady state, but it is the K effective would be larger in an accident or a nuclear device, and it would be less than 0 for a subcritical system. So here we have turned my analysis of an infinite medium, very large medium, into a medium that has a finite dimension, the finite radius, a finite volume, a finite mass. So we are going to use our derivation of that criticality equation to determine a critical radius, say for a sphere, or a critical length or volume or mass for a cube, a cylinder, or any shape that we are interested in. So 1 divided by 1 plus L square B square is now the thermal non-leakage probability. And another form of the criticality equation is that K effective should be equal to the infinite medium multiplication factor, which we defined by the 4-factor formula, eta epsilon PF multiplied into 1 divided by 1 plus L square B square. Now, as I said, K effective is equal to 1. That's a critical reactor. That's steady state, safe power generation. Larger than 1, that's a supercritical system. And less than 1 is a subcritical system where we don't have a chain reaction occurring in general. All right, so we define the criticality equation. Oh, the next thing, of course, is to solve that criticality equation. Solve it for what? For the flux. And again, we meet here a situation that looks like it has an analogy in the simple harmonic oscillator or the tuning circuit. We call that del square phi over phi the geometric buckling. So it depends on the geometry. Let's use the scissors rule, multiply both sides. So, oh, look at this. We get now a second order differential equation again with a Laplacian, but instead of in a non-multiplying medium getting a positive sign, oh no, today now with a multiplying medium, we get a negative sign. We get a negative sign in a non-multiplying medium. And that implies immediately that as we did the analysis in the previous chapter, that it has to be a harmonic solution, not the exponential growth and decay solution when we had the positive sign. So the fascinating thing is that the nuclear reactor is an analog of a harmonic oscillator, but it's in space because it's not x double dot d square x by dt squared, but it's a simple harmonic oscillator, you can call it, in space, because the Laplacian is a space type XYZ kind of operator. So we take again the spherical geometry. We like here to use the spherical geometry so that we can compare the behavior of neutrons in a vacuum. In a non-multiplying medium, we solved that in the previous chapter. And today, now, in a multiplying medium. We're not going through the drudgery of making the substitution or change of variables of WR over R for the flux. We know already that phi of R is some function W of R divided into R. So the solution for the spherical geometry, in the same way that we had in the case of a non-multiplying medium, would be 1 over R and 1 over R. Wonderful. But then that solution here has a negative sign. So it is not an exponential growth and decay solution. Oh, it is a harmonic solution, or an A cosine plus a C sine. And if you don't believe it, so go and take the first derivative of that whole solution, take the second derivative, substitute it in the differential equation here, you'll find that that solution indeed satisfies a differential equation. If you are a mathematician, then we start proving first the existence of that solution. And we spend lots of time doing that. And we also spend time proving that it converges to the actual differential equation. And basically, that is where the task of the mathematicians lies. For engineers, we are real life problem solving people. So we need to establish now what is the value of A and C, the concepts of integration, and we seek real life or practical solutions. So that A cosine for the spherical geometry, of course, you know that the cosine peaks and then comes down and then fluctuates, but we're going to be interested in the main harmonic, so we'll take only the first part of the cosine curve. So the question is, what is A and what is C? And if the flux is finite through the reactor, at the origin, you'll find that sine R over R is finite. But if you take at the origin the cosine BR over R when R is equal to 0 at the origin, cosine of 0 is 1, and at the origin R is 0, it gives you infinity. So it gives us here some kind of a dilemma. Can the flux be infinite in the same way as when we saw the solution for a non-multiplying medium? No, the flux cannot be infinite. It cannot have an infinite number of particles, neutrons, crossing unit area per unit time. So immediately we drop that cosine R over R solution. We say basically that A is equal to 0, and we adopt the solution of C sine BR over R as our solution for the neutron flux that happens in a sphere, a spherical geometry. So it is not the negative exponential as a function of R divided into R, like in a non-multiplying medium. No, it takes the shape of a sine R over R. And if you plot yourself by hand, maybe or in a hand calculator or computer program sine R over R, it looks very much like the cosine, except that it is the sine really divided into R. That is not all. We still are left with two constants of integrations to determine what is a C and what is the B here in the sine function. And as R tends to 0, you'll find that basically you get sine of 0 is 0, R is 0. 0 divided into 0 is not 1. 0 divided into 0 mathematically is not 1. To determine what is sine R divided into R as R tends to 0, we apply from mathematics what's called L'Hopital rule. L'Hopital seems to be a French scientist. The name L'Hopital is hospital, basically, rule. So he takes basically the derivative of the numerator and the derivative of the denominator as the limit of R tends to 0. So what's the derivative? dr by dr, it's 1. The d by dr, c sine bg sub r is c. And then you get the cosine of b sub gr. And then you take the derivative of b sub gr, that is bg. And as r tends to 0, the cosine tends to 1. So 1 and 1 here. And you end up with that the flux at the origin at R is equal to 0 is equal to C multiplied into B sub G, the geometric, so square root of the geometric buckling. And you get a distribution for the flux, as the flux now is going to be the value of the flux at the center, P sub 0, R is equal to 0. And then you get the sine B sub G R divided into B sub G R. So the distribution of the flux in a nuclear reactor now as a function of R from the center to the boundary is a sine R over R solution. All right, so that will help us determine the power, because we want really to eventually get the power distribution. If you multiply the flux into the macroscopic fission cross-section, you get the fission rate. If you multiply later on by the energy released by fission, you get the energy release per unit time, and that is the power. That's why we are seeking that kind of solution. We need also to determine what is the value of the geometric buckling, because that is an eigenvalue equation, and you can consider that the buckling is the eigenvalue of the equation. In that case, we have to apply another boundary condition to our second order differential equation. The neutron flux peaks at the center of the reactor according to that distribution. Sine R over R looks like a cosine that peaks at the center. But the neutrons at the boundary do not become totally 0. Some neutrons leak beyond the surface of the reactor by a small distance d. So we call the radius of the reactor the sphere in that case. Remember, we are dealing with spherical geometry, plus some distance. We call this the extrapolation length. We call this the extrapolated radius or the extrapolated boundary. So, and we can calculate that extrapolated boundary from the more advanced transport theory as 2/3 the transport mean free path. Some people take it as 0.71. the transport mean free path. We're going to use those values when we deal with a numerical example. For the cosine distribution, you'll find that at the extrapolated boundary, then the sine curve should become 0. And if you take the sine curve, it fluctuates, goes up and down, up and down, up and down. And every pi, it becomes 0, every value of pi. So at n pi, that argument of the sine curve, the angle b sub g r extrapolated should be equal to n pi. However, we are really only interested not in the fluctuations of the flux or the transient type of a flux. We are interested in the steady state. So what we are really interested in is in the main harmonic for the solution, which is n is equal to 1. And that immediately tells me that the geometric buckling should be equal, the geometric buckling multiplied by the extrapolated length should be equal to n1 and pi. And that b sub g now is equal to pi over r, the extrapolated boundary. So we go back to our solution for the flux in a spherical reactor and write that the flux as a function of distance is the value at the center decreasing all the way to the extrapolated boundary as sine pi over r, pi r divided into the extrapolated boundary. If the extrapolated boundary is small, we can just take that capital R as the boundary of the reactor itself. For instance, a pressurized water reactor would be 200 centimeters in radius. The extrapolated length would be 2 centimeters. So we can substitute for that R extrapolated as 200 and ignore the extrapolation length. For small reactors, you have to take that into account in general. All right, so let us then deal with our spherical geometry before we go back to this other equation. Remember when we wrote the expression for the infinite medium multiplication factor, we said that is equal to the infinite medium multiplication factor multiplied into a fast non-leakage probability multiplied by a thermal non-leakage probability. If you want to deal with an improved form of the criticality equation, in the same way that they said that the thermal non-leakage probability is 1 divided by 1 L square B square, and L square in that case depends on the thermal neutrons, we can suggest that the non-leakage probability for the fast neutrons is 1 plus B squared multiplied into a factor that has the dimension of centimeter squared, like L squared, but they only pertain to the fast neutrons. And interestingly enough, that tau here is called the Fermi factor, and Fermi made a mistake. He thought that it has dimensions of time, so he called it basically the tau factor here, or the Fermi age factor. Notice the word age, he thought it was time. The tau here stuck to it, but it is really the L squared for the fast neutrons. Okay, multiply those two terms into each other, you find that you get an L squared B to the 4th power. Now, for a large reactor, like a pressurized water reactor or boiling water reactor, we said that B is equal to pi over the radius. And B to the 4th power would be even smaller than B squared. So we can ignore that term here, the B to the 4th power, and say that my effective multiplication factor is equal to K infinity divided by 1 plus M squared B squared, where that M squared now is L squared, the diffusion area for thermal neutrons, and tau is the Fermi age. Fermi age, it has dimensions of centimeter squared, and that M squared represents basically the square of the distance traveled by the neutrons being born in fission, then leaking from the reactor at thermal energies as well as fast neutrons. So that's what's called the modified two-group theory for criticality conditions. Wow, wonderful. So we know how to determine now the critical dimension of a reactor. Remember, the criticality condition is material buckling should be made equal to the geometric buckling. But we are manipulating that equation and adapting it to the design of a nuclear reactor. All right, we come back to the material buckling. Let's take the material buckling is k infinity minus 1 divided into m squared. And the geometric buckling for a sphere, as we derived a few moments ago, is pi over the extrapolated length squared. Oh, if I know the k infinity and I know the m squared, then I can determine what is the extrapolated radius at steady state. So that becomes the critical dimension of the reactor. And that is going to help me design the size of a nuclear reactor, given that I have a geometric, a material composition of uranium enriched to a certain level, a moderator or a coolant, water or heavy water or beryllium or graphite. And in that case, just solving for the R extrapolated radius, bringing it to this side and taking the square root, you find that we can determine what is the extrapolated radius for a nuclear reactor to be critical. And definitely the actual radius would be the extrapolated radius minus that the extrapolation lengths, and the square root of m squared is m. So we have an equation now for the radius of a nuclear reactor of a given composition expressed in k infinity that would give me basically a critical reactor in general. And all that mathematics, of course, is necessary to understand how to design a nuclear reactor. But let us simply go and design one and compare it to some experimental values. Obviously, in the one group diffusion equation, the data that we use in designing reactors is tabulated in different sources, databases. One of them is ANL 5800. That's a report by ANL. ANL stands for Argonne National Laboratory. You find that the data that we use in the design can be inferred for different fuels. For instance, if you have plutonium-239 that nu in the regeneration factor is 2.98, it's higher than for uranium-235, 2.6, or uranium-238 at 2.6. The fission cross-section, though, in bonds for plutonium-239 is 1.85 and uranium-235, 1.40. You notice that plutonium has a higher number of neutrons per fission event, and fission cross-sections is higher. And we'll see later, that means that the critical mass for plutonium is going to be less than the critical mass in uranium-235. We have the capture cross-section and the transport cross-section tabulated for us to use in a calculation. Let's do a calculation that puts all the theory that you spent really so far, at least 3.5 hours developing. And first, we're going to apply it to a situation that we have a fast reactor. Why fast reactor? Because we are not going to allow for the presence of the moderator. And that represents basically a critical experiment that people have conducted, and we can compare their results for the two. Let us first assume that we have basically a sphere of uranium-235. And for uranium-235 to have a no moderator, we take the cross-sections only in the fast region where the neutrons are below 2 million electron volt, but not thermal neutrons. In that case, the absorption cross-section is 2.840. The transport microscopic cross-section is 8.2. This data is from a reference, Wirtz, a book that a German scientist, Mr. Wirtz, wrote for the design of fast reactors, where sodium is cooled as a coolant. We need the density of uranium-235. That's 18.75 gram per centimeter cube. And the product of nu sigma f for fast neutrons. You notice that it's not the southern bond that we get when we have thermal neutrons. This is a fast neutron because it's only a sphere of uranium-235. It has no moderator. No moderator means it's a fast neutron reactor, or fast reactor value is very low. And the difference between the nuclear program in the Second World War and the German program is that the Germans thought that they can only obtain fission in a moderated system, where you get basically here the fission cross-section in the southern bonds. Whereas Enrico Fermi and the people working in the United States thought, no, we can get a critical system, even if we deal with fast neutrons, there is no moderator in the system. And that made a big difference. The Germans tried to build a large reactor, and they concluded that any nuclear device would be tremendously large in size, like 2 meters in diameter, whereas in the United States, that was achieved according to what we are going to do right now. Let's assume that we are dealing only now with fast neutrons. So the L square thermal does not apply, and the geometric buckling for a sphere would be pi over r critical square. And the geometric buckling now is the radius of the reactor. We want to determine what is the radius of the reactor that would match the material buckling. So the material buckling and the geometric buckling, as you could see here, that's why we call it the criticality equation, are being made, forced to be equal. So you either change the material compositions and determine the critical radius, or you modify the radius, like in the Chicago pile number 1, when they were adding pile upon pile of the uranium mixed with the graphite. And in that case, you determine what is the material composition in general. We are going to replace the migration area for a neutron reactor that have both fast and thermal neutrons by simply the fast non-leakage probability, which may be determined by the Fermi age. Now, equating the geometric buckling to the material buckling gives us these two terms here, where we can use a scissors rule and immediately determine that the critical radius for that material with that composition here, k infinity minus 1 over L squared, is equal to pi, the square root of L squared, the square of the diffusion length for fast neutrons, divided into k infinity minus 1. All right, so what is L squared here for the fast neutrons? Is a diffusion coefficient divided by the macroscopic absorption cross-section. The diffusion coefficient, we said, can be calculated from the more advanced transport theory as 1 divided into 3 times the macroscopic transport cross-section. And if you have a pure sphere of uranium, you don't have a moderator, you don't have a structure. So basically the fuel utilization factor has to be equal to 1, because the absorption in the fuel divided by the absorption in the whole system is only in the fuel. So it is equal to 1. If you further take P as equal to 1 and the epsilon is equal to 1, then we know what is the value of K infinity. K infinity now becomes the regeneration factor multiplied by epsilon P and F, which are all 1s. So it should be equal to nu sigma F, which is given to us in the problem as 5.297 neutrons barn, divided into the absorption cross-section 2.8, and we get an infinite multiplication factor of 1.86. That is if I have an infinite medium. But we are dealing with a finite medium. And because we are dealing with a finite medium, we have the leakage from the surface of the medium. The larger the radius, obviously, the less the leakage from the surface of a sphere, because the surface area of a sphere is 4 pi r squared divided into the volume of a sphere, 4/3 pi r cubed. So it is proportional to 1 over r, the radius of the sphere. Okay, so that is the K infinity in our equation here, K infinity. We need to determine what is L squared F for a sphere of uranium-235. Well, in that case, we have to calculate the number density, which is rho Avogadro over m. Notice here we are using our modified form of Avogadro's law, multiplied into the transport microscopic cross-section. And you see why we write for Avogadro's constant 0.6 10 to the 24, because our microscopic cross-section 8.24 here is in barn, so that's 10 to the minus 24. And when you write Avogadro's number as 0.6 10 to the 24 rather than 6 10 to the 23rd power, that plus to the 24 and minus 24 cancel out, and you get that the macroscopic transport macroscopic cross-section is 0.396 centimeter minus 1. That allows me to calculate the diffusion coefficient. So L squared for the fast neutrons is d over sigma A, and the sigma A is the number density of the uranium, 18.75 divided into 235 multiplied by 0.6 10 to the 24. I've approximated the mass of uranium here as 235, and we are given the absorption cross-section So you find that the absorption cross-section, microscopic absorption cross-sections is 0.137 centimeter minus 1. And L square is d over sigma A. It is 1 over 3, the transport macroscopic cross-section, the absorption macroscopic cross-section. So L square is 6.144 centimeter square. Going back to the criticality equation, R sub C now is L squared divided by K infinity minus 1. We can calculate the critical radius of our uranium-235 sphere as pi, the square root of 6.144 divided into 1.86 minus 1. And it gives us pi, the square root of 7.1. And pi is, of course, 3.151519. It gives us a radius as 8.4 centimeters. So that would be the radius of a sphere of pure uranium-235. We don't stop there in the design. In the design, we go and calculate the volume. So what is the volume of a sphere? Well, we all know that. It's 4 pi, the radius cubed divided into 3. So you take that 8.4 centimeters, calculate a critical volume. So we calculated here a critical radius, and we calculated here a critical volume, 2,400 centimeter cube. While the last step in the design is to calculate what is the critical mass. How do we calculate the critical mass? It's very simple. You multiply your critical volume by the density of the uranium, 18.75, and you get 46.5 kilograms. And that was, interesting enough, almost the size of the critical assembly or the atomic bomb that was dropped on Hiroshima. Remember, it was uranium-235, going back to our first chapter or second chapter. And in fact, it was built as an experiment. Many experiments were built. Some of them, one of them in particular that relates to what we have done today, is named the Godiva experiment. Godiva, if you go to your English classes, was the wife of one of the warlords in the UK, and he imposed very high taxes on his subjects. So Lady Godiva protested that. She had very long hair by riding bear on a horse. So they named the first experiment, critical experiment using uranium-235, they called it Godiva. And notice here the core radius. The actual core radius for criticality was 8.71 centimeter. What does our calculation give us here? 8.39 calculation. So you could see that there is a good match between the critical radius from our calculation and the actual critical radius of the experiment using uranium-235. Why was it called Godiva? Because it doesn't have a reflector. If you add a reflector around that uranium-235, we can reduce the critical mass by having neutrons reflect back from the reflector back to the center. Another experiment using plutonium-239, which would be the Trinity experiment or the device that was dropped on Nagasaki, that would be smaller, as I suggested, 6.28 kilograms, centimeters, the critical radius. They built other experiments, for instance, here, different enrichment in uranium-235, even using uranium-233 is even a smaller critical mass than plutonium-239 with different effective multiplication factors. And then they built an experiment called the Zero Power Reactor number 3, ZPR, which was 30 centimeter of uranium, and the core radius was now large, 47.74 centimeter. And that was not pie in the sky. This is an actual experiment. That is the experiment that it was named Jezebel, which was a plutonium-239. And they're experimenting here in checking the theoretical calculation that we have done in a few moments ago by bringing in hemispheres on a wire with basically a machine, obviously from a distance. And they have here different cylinders of plutonium-239, and they keep adding from the top and the bottom parts of plutonium-239. In that case, you have a critical configuration, so they can check the theory to the actual experiment in general. I described to you here the Jezebel sphere. We had a gentleman from the Los Alamos National Lab who visited us recently, and he suggested, suggested that they are still making checks of on supercomputers, in that case, of experiments on the Jezebel experiment very recently in 2016. They determined basically that the critical mass changed from 16.45 to 16.57. So critical masses basically are checked both on experimentally as well as calculationally. And the variable there is the measurements of the cross sections that we measure in that case. So what we did today is solve the equations in a non-multiplying medium and solve the equations for neutron transport in a multiplying medium. And we accessed the secret of the nuclear age. And the secret is very simple. You create a match between the geometry and the material compositions. Basically, you equate the geometric buckling to the material buckling. And we reached the limit of our class today. I'll give you some examples that you can work on. And here, our example here for the critical mass calculation will be duplicated maybe for a plutonium sphere, the Jezebel experiment. And you'll see that we can get some pretty good results from calculations on what the experiments show us, but there is no way of avoiding checking the theoretical calculations with experiments. I'll stop sharing, but I'll be available the rest of the afternoon is necessary in the chat room for questions.